What if the greatest obstacle to returning from Mars isn't technology, but the human body itself? For decades, we have imagined Mars as a destination, a frontier, a challenge to be overcome with better rockets, stronger shields, smarter machines. But what if the truth is far more unsettling? What if the first humans who set foot on Mars are not pioneers who will return, but the first humans whose bodies will never again belong to Earth? Mars is not distant in the same way the Moon is distant. The Moon is a nearby outpost 3 days away, close enough that rescue is always conceivable. Mars is something else entirely. Even under ideal orbital alignment, a journey to the red planet takes 6 to 9 months in one direction. A complete mission, including surface operations and return, stretches into 2 or even 3 years away from Earth. During that entire time, the crew exists beyond the reach of help. There is no emergency evacuation, no real-time communication, no medical rescue that can be dispatched when something goes wrong. At its closest point, Mars remains more than 55 million kilometers away. A single distress message takes over 20 minutes just to reach Earth and another 20 to receive a reply. If a crisis unfolds, assistance does not arrive late. It does not arrive at all. Yet, even this extreme isolation is not what ultimately turns a Mars mission into a one-way journey. Distance alone does not seal the astronaut's fate. The real danger begins much earlier, far more quietly inside the human body itself, long before anyone ever steps onto Martian soil. The human body is not adaptable in the way science fiction often promises. It is not a flexible machine that simply recalibrates to any environment we place it in. It is, instead, a biological system exquisitely tuned to one very specific set of conditions. One gravity, one magnetic field, one radiation shield, and one long evolutionary history shaped entirely on Earth. The moment we remove the body from that context for extended periods, something profound happens. The mechanisms that once strengthened bone, muscle, and cardiovascular function begin to reverse. Instead of building and maintaining, the body starts to conserve, dismantle, and simplify itself. What evolution spent millions of years refining, the absence of Earth's conditions, quietly begins to undo. A Mars mission forces the body through 3 incompatible gravitational regimes. First comes prolonged microgravity during transit, where the body no longer senses weight at all. Then comes life on Mars, under just 38% of Earth's gravity, enough to feel present, but not enough to fully load the body's systems. And finally, if a return is even attempted, the body must once again confront full Earth gravity. Each transition alone is stressful. Combined over years, their effects may become irreversible. We already see a warning sign. Astronauts returning from the International Space Station often struggle to walk after only 6 months in orbit. A Mars mission multiplies that exposure several times over, pushing the human body far beyond the conditions it was ever designed to survive. The most lethal threat in deep space does not arrive as an explosion or a sudden failure. It does not announce itself with alarms or fire. It works in silence. It works constantly. And it remains invisible to human senses. That threat is cosmic radiation. Here on Earth, life exists inside a protective cocoon. A powerful magnetic field deflects charged particles, while a thick atmosphere absorbs what remains. Together, they block more than 99.9% of high-energy radiation before it ever reaches our bodies. We rarely think about this shield, because we have never lived without it. Beyond Earth orbit, that protection disappears almost entirely. A Mars-bound astronaut is exposed to a continuous storm of galactic cosmic rays and solar particle events, day after day, month after month. Over the course of a full mission, the accumulated dose reaches between 870 and 1200 millisieverts. That is roughly 700 times the annual radiation dose experienced on Earth, equivalent to hundreds of CT scans or thousands of X-rays delivered slowly, relentlessly, and without pause. At these levels, radiation does not merely increase risk. It alters biology. DNA strands break and repair imperfectly. Brain tissue shows measurable, structural, and functional changes. Blood vessels stiffen and age decades ahead of schedule. The immune system weakens as bone marrow is damaged at the cellular level. According to NASA data, cancer risk rises by 5 to 10%. While cognitive decline, memory loss, slowed thinking, impaired decision-making may become permanent. There is no practical shield against this environment. Adding mass does not solve the problem. Thick walls generate dangerous secondary radiation that can worsen exposure rather than reduce it. Radiation in deep space is not a wound that heals. It is a slow rewriting of the biological blueprint, one cell at a time, until the body that returns is no longer the body that left Earth. Gravity is not merely a physical force acting on the body. It is a biological signal. Every step taken on Earth sends a constant message to the skeleton. You are needed. You must remain strong. Bone is living tissue, continually rebuilt in response to stress. Remove that stress, and the message changes. In microgravity, the balance that maintains skeletal strength collapses. Bone formation slows dramatically, while bone resorption, the process by which bone is broken down, continues almost unchecked. The result is a steady, relentless loss of structural integrity. Astronauts lose between 1 and 3% of their bone mass every month in weightlessness. At first, the numbers seem abstract, but over time, they become devastating. After 6 months, bone loss can reach 18%. After 1 year, more than a third of the skeleton's density may be gone. Over the course of a 2-year Mars mission, losses exceeding 50% are possible. For comparison, elderly patients suffering from severe osteoporosis have typically lost only 30 to 40% of their bone mass. A healthy astronaut in their 30s could return with bones weaker than those of a fragile elderly patient. The damage concentrates in the very bones required for upright life on Earth: the hips, the femur, and the spine. These are the structures that bear weight, absorb impact, and keep the body standing against gravity. As bone dissolves, calcium leaches into the bloodstream and is excreted through the kidneys, dramatically increasing the risk of painful kidney stones. The skeleton does not merely weaken in space. Deprived of its gravitational signal, it quietly reclassifies itself as unnecessary and begins to dismantle itself from within. Muscles exist for one fundamental purpose: to resist gravity. Every movement on Earth, from standing upright to simply breathing, forces muscle fibers to work continuously against weight. Remove that constant resistance, and muscles begin to lose not only their strength, but their identity. In microgravity, muscle loss mirrors the decline seen in bone, at a rate of 1 to 3% per month. But the damage goes far deeper than shrinking size alone. At the cellular level, muscle fibers begin to change type. Slow, endurance-oriented type I fibers, the fibers that allow humans to stand, walk, and remain active for long periods, gradually convert into fast, fatigue-prone type II fibers. These fibers may contract quickly, but they tire easily and are poorly suited for sustained activity under Earth's gravity. For life back on Earth, this shift is catastrophic. Astronauts returning from space missions report profound weakness. Climbing stairs becomes exhausting. Simple tasks demand conscious effort. Balance deteriorates as stabilizing muscles fail to respond with the precision they once had. The damage does not stop with muscle tissue. Joints begin to degrade as well. Without regular mechanical loading, cartilage thins and loses its resilience. Tendons weaken, and the natural shock-absorbing systems of the body begin to fail. What unfolds is accelerated aging, a process that normally takes decades, compressed into a matter of months. Even aboard the International Space Station, where astronauts exercise for 2 hours every day using resistance devices, this deterioration can only be slowed, never fully prevented. Mars, with just 38% of Earth's gravity, offers too little mechanical stress to reverse the process. The muscles that arrive on Mars are already aging rapidly, and they continue to age and fast forward long after touchdown. The heart is not just a pump. It is a muscle shaped, trained, and maintained by gravity itself. On Earth, every heartbeat must work against a constant upward resistance, pushing blood from the chest to the brain. That continuous struggle is what keeps the heart strong, efficient, and resilient over a lifetime. In space, that resistance vanishes almost instantly. Without gravity pulling blood downward, fluids shift toward the upper body and head. Faces swell, legs thin. The body misinterprets this redistribution as fluid overload and responds by shedding blood volume. As circulating blood decreases, the heart adapts to a lower workload, and like any muscle that is no longer challenged, it begins to shrink. Studies of long-duration spaceflight show that astronauts can lose up to 20% of their heart mass. The heart literally becomes smaller and weaker, optimized for an environment where it no longer needs to fight gravity. This adaptation is efficient in space, but disastrous for a return to Earth. When gravity is reintroduced, blood pressure collapses. Dizziness becomes common. Many astronauts experience fainting when they attempt to stand a condition known as orthostatic intolerance. After 2 to 3 years on a Mars mission, this effect would likely be far more severe. The heart may be physically incapable of generating enough pressure to lift blood to the brain. Combined with radiation-induced damage to blood vessels, stiffened arteries, impaired endothelial function, increased stroke risk, the danger becomes existential. The cardiovascular system is no longer calibrated for Earth. The heart has adapted to a different world. It has, in every meaningful sense, learned a new planet. For decades, artificial gravity has been proposed as the solution to humanity's biological limits in space. Concepts range from rotating spacecraft to large centrifuge habitats designed to simulate the constant pull of Earth. On paper, the physics is sound. In practice, none of these systems are operational, tested, or remotely ready for multi-year deep space missions. Creating artificial gravity requires rotation at precise speeds and scales. Rotate too slowly, and gravity is too weak to matter. Rotate too quickly, and the human inner ear becomes overwhelmed, triggering severe motion sickness, disorientation, and nausea. To achieve Earth-like gravity without debilitating side effects, a structure must be enormous, far larger than anything humanity has ever built or launched into space. Engineering challenges multiply rapidly. Rotating structures experience intense mechanical stress. Bearings must operate flawlessly for years without maintenance. Energy demands rise sharply. Structural failure is not an inconvenience. It is catastrophic. Even short-arm centrifuges tested so far have shown mixed physiological results and introduce new medical uncertainties. As of today, no system exists that can safely provide continuous, Earth-equivalent gravity for years at a time. Until that reality changes, the biological trajectory of a Mars mission remains fixed. The human body will continue to adapt away from Earth, not back toward it. Mars missions, under current technology, are not round trips. They are biological transformations, slow, permanent, and profound. After 2 to 3 years beyond Earth, the human body is no longer the same organism that left it. DNA has been altered by relentless radiation. Bones have grown porous and brittle. Muscles have weakened and lost their endurance. The heart has shrunk, adapting to an environment where gravity no longer demands its strength. Even the brain may have changed in ways that cannot be fully reversed. In that condition, returning to Earth would not be an act of triumph. It would be an act of risk. Standing upright could trigger fractures. A weakened cardiovascular system might struggle to deliver blood to the brain. Cognitive changes could impair judgment, at the very moment survival demands clarity. What we often imagine as a heroic return could, in reality, be dangerous, possibly fatal. From our perspective at Deep Space Inquiry, this leads to a deeper and more unsettling question. Are we truly prepared to accept that becoming a multi-planet species may require bodies that no longer belong to their planet of origin? That exploration, at this scale, may come with permanent biological consequences? The first humans on Mars may not be explorers who come home to tell the story. They may be settlers not by choice or ambition, but by necessity shaped by the journey itself into something no longer fully earthbound. And that may be the true cost of reaching another world. At Deep Space Inquiry, we don't chase spectacle. We follow questions to where they become uncomfortable. If the universe teaches us anything, It is this: progress is not just about how far we can go, but what we are willing to become along the way. Mars will not just change where humans live. It may change what it means to be human, and that truth lingers long after the rockets fall silent.